Deep in the vast ocean of space, where reality twists and bends in ways that defy imagination, there exists a force so powerful it can warp the very fabric of the cosmos, yet you can't see it. Picture a pulsar, the spinning corpse of a dead star, its magnetic field so intense it distorts space-time itself, sending ripples through the universe like a stone dropped into a cosmic pond. This is just one glimpse of the invisible hand guiding everything around us. Magnetic fields. They're the silent architects of the universe, weaving through galaxies, sculpting stars, and even cradling the conditions that made life possible on our tiny blue planet. And yet, for something so fundamental, most of us barely notice they're there. Think about that for a moment. Every time you've marveled at the northern lights dancing across the sky, or felt the pull of a compass needle pointing north, you've witnessed just a whisper of their power. But out there, beyond our atmosphere, magnetic fields are performing feats that border on magic. They accelerate particles to nearly the speed of light, carve colossal jets of plasma stretching thousands of light years, and even shield entire solar systems from the deadly radiation of deep space. These forces don't just exist, they shape the fate of everything from the smallest atom to the largest supercluster of galaxies, and that's just the beginning. Over the course of this journey, we're going to uncover 30 astonishing ways magnetic fields orchestrate the cosmos, each more mind-bending than the last. You'll discover how they birth stars in stellar nurseries, why they're the reason some planets have auroras while others are barren wastelands, and how they might even hold the key to unlocking the mysteries of dark matter. This isn't just a story about invisible lines of force. It's about the hidden symphony playing beneath the surface of reality, a symphony we're only just beginning to understand. So buckle up, because by the time we're done, you'll never look at the universe the same way again. Deep in the silent void of space, some of the universe's most terrifying predators don't hunt with claws or teeth. They strike with pure, invisible force. Meet Magnetars, the undead royalty of cosmic horror. These aren't your average neutron stars. Imagine crushing the mass of two suns into a ball smaller than Manhattan, then spinning it faster than a blender blade while wrapping it in a magnetic field so strong it could rip the iron from your bloodstream from halfway across the solar system. That's a magnetar, nature's ultimate electromagnet, with fields measuring a quadrillion times stronger than Earth's. One particularly infamous specimen, SGR 180620, gave us a front-row seat to their destructive power in 2004. For just 0.2 of a second, it unleashed a gamma-ray burst so violent that despite being 50,000 light-years away, it actually compressed Earth's ionosphere, the layer of our atmosphere that bounces radio signals. If that flare had happened within 10 light-years of us, our ozone layer would have been shredded, bathed in enough radiation to trigger mass extinctions. But here's the chilling part: magnetars don't even need direct hits to kill. Their mere presence warps space-time so severely that any nearby planet would experience tidal forces strong enough to liquefy its crust. Picture a world where the ground beneath your feet writhes like ocean waves as the magnetar's gravitational grip stretches and squeezes it relentlessly. These monsters don't just destroy worlds, they play with them first. And scattered across our galaxy, astronomers estimate there could be tens of millions of these lurking predators, each one a cosmic sword of Damocles waiting to flicker awake. The sun doesn't just give us light and warmth, it also fires bullets of pure magnetism straight at us. Every so often, tangled knots in the sun's magnetic field snap like overstretched rubber bands, hurling billion-ton clouds of charged particles into space at millions of miles per hour. These coronal mass ejections are cosmic storms of raw electromagnetic fury, and without Earth's invisible force field, the magnetosphere, they'd cook our planet to a crisp. Think of it as a galactic game of dodgeball, where our magnetic field bends and deflects the worst of the sun's tantrums, channeling charged particles harmlessly toward the poles to create shimmering auroras instead of scorching our surface. But sometimes the sun throws a fastball we can't fully handle. Take the Carrington event of 1859, when a solar storm so powerful it set telegraph offices on fire, yes, literally set them ablaze, ripped through Earth's defenses. Operators got shocked through their equipment, sparks flew from disconnected wires, and auroras lit up skies as far south as Cuba. If that happened today, our hyper-connected world would reel, satellites would tumble out of alignment, GPS systems would fail, and power grids could collapse under the surge, leaving cities dark for weeks or even months. And here's the unsettling truth: we're more vulnerable now than ever. Modern technology practically hands solar storms a roadmap for chaos. Undersea internet cables orbiting spacecraft, even the microchips in your phone, all are at risk from these magnetic tsunamis. Scientists warn another Carrington-level event isn't a matter of if, but when. The only question is whether we'll be ready when the sun next flexes its magnetic might and reminds us just how fragile our electronic lifelines really are. If you could see the Milky Way through magnetic vision, our galaxy wouldn't look like a swirling disk of stars. It would resemble a colossal spiderweb, its threads glowing with invisible energy. These are the galactic magnetic skeletons, vast networks of force stretching tens of thousands of light years, weaving through spiral arms like cosmic stitching. Far from being passive bystanders, these fields are master sculptors, shaping the very architecture of galaxies. Take those iconic spiral arms we see in pictures. They're not just pretty swirls. Without magnetic fields, they might not exist at all. Here's how it works. As gas and dust swirl through a galaxy, magnetic fields act like invisible highways, channeling material into dense ribbons where gravity can take over. These become the nurseries for new stars, with magnetic pressure helping to compress clouds until they ignite into stellar fire. The Milky Way's polarized light maps reveal this hidden framework: filaments of magnetism aligning dust particles like compass needles, creating patterns that ripple across entire galactic neighborhoods. Picture sprinkling iron filings around a bar magnet, then scaling that up to galactic proportions. But the real magic happens in the details. Some regions, like the Orion Molecular Cloud Complex, show magnetic fields so strong they can literally stall star formation by propping up gas clouds against gravity's pull. Elsewhere, fields twist into helical coils, launching jets of newborn stars along magnetic corridors like pearls on a string. Even more astonishing, these galactic skeletons might solve a long-standing mystery: why some galaxies, like our own, keep forming stars for billions of years while others burn out young. The answer could lie in how delicately or violently a galaxy's magnetic web stirs its cosmic ingredients. So next time you gaze at the Milky Way, remember, you're not just seeing stars. You're witnessing the ghostly fingerprints of magnetism, a force that built the scaffolding of our galactic home and continues to shape its destiny, one invisible thread at a time. Before a star bursts to life, it begins as a whisper in the dark, a cold, dense pocket of gas floating through a molecular cloud, waiting for gravity to pull it together. But without magnetic fields, this fragile process would spiral into chaos. Imagine trying to collapse a vast, fluffy cloud directly into a tight, glowing sphere. The material would fragment into countless pieces long before a star could ignite, like a collapsing building crumbling into rubble instead of forming a solid foundation. That's where the universe's invisible scaffolding comes in. Magnetic fields wrap around these stellar nurseries like cosmic cocoons, channeling and restraining the collapsing gas with lines of force. As gravity pulls material inward, the field resists, slowing the collapse just enough to prevent catastrophic fragmentation. This delicate balancing act is called ambipolar diffusion, a process where neutral particles slip between magnetic field lines like beads on a string, drifting slowly toward the center while the ionized material remains anchored to the magnetic web. It's nature's way of ensuring a controlled, steady fuel supply for the newborn star, rather than a messy free-for-all. Some of the most striking evidence comes from observations of the Taurus molecular cloud, where astronomers have mapped magnetic fields threading through star-forming regions like celestial stitchwork. These fields align dust grains, polarizing the light that passes through and revealing patterns that resemble giant fingerprints, each one a roadmap of forces guiding stellar birth. Without this magnetic regulation, star formation would be wildly inefficient, scattering potential suns into useless fragments. But the real magic happens in the details. In regions where fields are especially strong, like the famous pillars of creation, towering columns of gas defy gravity's pull for millennia, held upright by magnetic pressure like sculptures frozen in time. Elsewhere, fields twist into helical coils, funneling material into spinning disks that will one day birth planets. It's a dynamic, ever-changing dance, one where magnetism doesn't just assist star formation but actively choreographs it, ensuring each new sun gets the right start in life. So the next time you look up at the night sky, remember, every star you see was once cradled in an invisible magnetic embrace, shaped by forces that balanced chaos with precision, turning scattered gas into the brilliant lights that fill our universe. At the heart of the galaxy Messier 87, a monster lurks, a supermassive black hole weighing as much as 6.5 billion suns. But its most spectacular feature isn't what it devours, it's what it spits out. Stretching 5,000 light-years into space, twin jets of plasma blast outward at nearly the speed of light, glowing like cosmic blowtorches. These aren't just random ejections, they're the universe's most powerful particle accelerators, and their secret lies in the invisible coils of magnetism wrapped around the black hole like a cosmic slingshot. Here's how it works. As matter spirals toward the black hole, it doesn't just vanish. Instead, it forms a swirling disk so hot and dense that atoms tear apart, creating a soup of charged particles. This ionized plasma becomes tangled in the black hole's magnetic field, which twists tighter and tighter as it's dragged inward. Imagine wringing out a wet towel until the tension snaps, except here, the towel is space-time itself. When the magnetic pressure becomes too great, it recoils violently, flinging jets of plasma along the black hole's spin axis like sparks from a spinning grindstone. But the real magic happens farther out. Those jets aren't just streams of hot gas, they're cosmic synchrotrons, natural particle colliders that whip electrons to near light speeds. As these charged particles spiral around magnetic field lines, they emit synchrotron radiation, a brilliant glow visible across the electromagnetic spectrum. The famous image of M87's jet captured by the Hubble Space Telescope shows this process in action, a fluorescent thread of energy powered entirely by invisible magnetic forces. And the scale is staggering. The energy in these jets could outshine entire galaxies, with particles reaching energies 1,000,000 times greater than anything produced in human-made colliders. Some even escape their host galaxy entirely, seeding intergalactic space with high-energy cosmic rays. Yet all this violence traces back to a simple principle. When you twist magnetic fields to their breaking point, the universe responds with some of its most breathtaking fireworks. What's even more astonishing is how these jets shape their surroundings. They carve bubbles in intergalactic gas, regulate star formation in their host galaxies, and even transport heavy elements across cosmic distances. Without them, the universe would lack the scaffolding needed to build the largest structures we see today. So the next time you see an image of a galaxy with brilliant jets stretching into the void, remember, you're witnessing magnetism pushed to its absolute limits, a force powerful enough to defy even the grip of a black hole. Earth's northern lights might steal the spotlight, but out in the solar system, auroras put on shows that make ours look like a dim porch light. Take Jupiter. The king of planets doesn't just have auroras, it has continent-sized light shows burning 1,000,000 times brighter than Earth's, powered by a volcanic moon caught in a cosmic tug-of-war. Io, Jupiter's pizza-colored satellite, spews sulfur dioxide into space at a ton per second, creating a donut-shaped plasma torus around the gas giant. As Jupiter's magnetic field whips this ionized soup around at 70 kilometers per second, the friction generates currents so strong they could power human civilization 1,000 times over. These charged particles then race along magnetic field lines, slamming into Jupiter's poles with enough energy to glow in X-rays, a light show invisible to our eyes but dazzling to telescopes like Chandra. Then there's Saturn, where the auroras aren't just circular, they're geometric. The planet's north pole boasts a permanent hexagon-shaped storm large enough to swallow 4 Earths, and its auroras trace this 6-sided pattern like neon outlines. Scientists believe Saturn's rapid rotation once every 10 hours twists its magnetic field into a complex knot, funneling charged particles in bizarre angular paths. Unlike Earth's fleeting curtains of light, Saturn's auroras can lock into these precise shapes for days, painting the sky with glowing polygons that defy conventional physics. But the real outlier is Uranus, the solar system's tipped-over oddball. Its magnetic field is so misaligned it looks like the planet got hit by a cosmic bumper car. Auroras here don't circle the poles, they flicker near the equator, appearing and vanishing as the magnetic field wobbles chaotically. These aren't just pretty lights, they're cosmic diagnostics, revealing how magnetic fields interact with solar wind in ways we're still struggling to decode. What unites all these phenomena is the same basic principle: magnetic fields as particle highways. Whether it's Earth's protective bubble or Jupiter's Io-fueled infernos, charged particles spiral along these invisible tracks, illuminating atmospheres like neon signs in a cosmic diner. The differences come down to scale and structure, a reminder that while magnetism works the same everywhere, its effects can range from serene glowing ribbons to storms that could vaporize a spaceship. In the chaotic dance of charged particles across the universe, there's a moment when magnetic fields don't just bend, they snap. This explosive breakup, called magnetic reconnection, is one of nature's most efficient energy converters, turning stored magnetic energy into blistering heat and supersonic plasma jets in the blink of an eye. Picture 2 rivers of magnetism flowing in opposite directions, their field lines pressed together like tangled rubber bands. When the tension becomes too much, they violently reconfigure, releasing energy equivalent to thousands of hydrogen bombs in seconds. This is the engine behind solar flares, those searing eruptions on the sun's surface that can unleash enough radiation to disrupt satellites and power grids across an entire hemisphere of Earth. One of the most striking examples occurred in 2017, when a series of reconnection events triggered the strongest solar flare in a decade. Satellites recorded X-rays screaming outward at nearly the speed of light, while loops of plasma larger than Earth arced hundreds of thousands of kilometers into space. But reconnection isn't just a solar phenomenon. Right here in our planet's magnetosphere, it fuels the dazzling auroras we admire and sometimes threatens the technology we rely on. During geomagnetic substorms, Earth's magnetic field lines stretch like overextended springs before suddenly snapping back, dumping charged particles into our upper atmosphere and painting the sky with otherworldly light. NASA, a magnetospheric multiscale mission, or MMS, has been studying this process up close with 4 spacecraft flying in tight formation. Their discoveries have upended old theories, revealing that reconnection isn't slow and steady, but erupts in frenetic bursts smaller than 100 kilometers across. These microexplosions accelerate electrons to nearly the speed of light, creating waves of energy that ripple through space. The data shows how thin sheets of electric current, no thicker than a few kilometers, become cosmic trigger points where stored magnetic energy transforms into kinetic chaos. What makes reconnection so fascinating is its universal nature. The same process that lights up Earth's skies also powers the relativistic jets of black holes and drives eruptions on distant stars. Even in laboratory fusion reactors, where scientists struggle to contain plasma at millions of degrees, uncontrolled reconnection can shatter containment in microseconds. Yet for all its destructive potential, this phenomenon might hold the key to unlocking clean energy if we can learn to tame it. Every flare, every aurora, every burst of cosmic radiation whispers the same lesson. When magnetic fields break and remake themselves, the universe doesn't just change shape, it ignites. A planet's fate isn't just written in its distance from a star, it's etched in invisible lines of magnetic force. Take Earth and Mars, two worlds born from the same cosmic neighborhood, yet one thrives with oceans and life while the other stands as a desiccated wasteland. The difference: a magnetic field. Earth's churning molten core generates a protective bubble called the magnetosphere, deflecting the sun's deadly radiation like an interstellar umbrella. Mars, though, lost its magnetic shield billions of years ago, and without that protection, solar winds stripped away its atmosphere molecule by molecule. Today, the red planet's air pressure is less than 1% of Earth, so thin that liquid water instantly boils away into the frigid void. But this isn't just a story of two planets. As we discover thousands of exoplanets orbiting distant stars, magnetic fields might be the silent gatekeepers of habitability. Imagine a world twice the size of Earth, orbiting snugly in its star's so-called Goldilocks zone. Without a magnetic field, even that prime real estate could turn deadly. Proxima Centauri b, our closest known exoplanet neighbor, faces this exact crisis. Bathed in relentless flares from its red dwarf sun, its atmosphere could be eroding at a rate 100 times faster than Mars, unless, like Earth, it has a magnetic shield holding the line. The data from NASA's MAVEN mission at Mars reveals the grim mechanics of atmospheric loss. Charged particles from solar winds slam into unprotected air molecules, knocking them into space like billiard balls. Over eons, this process can drain an ocean's worth of water vapor and vital gases. Earth's magnetic field doesn't just deflect these particles, it funnels them toward the poles where they ignite the auroras instead of wreaking havoc. Yet there's a tantalizing twist: some planets might regain their magnetic protection. Venus, though hotter than a pizza oven, shows signs of induced magnetism, a weak field generated by solar wind interacting with its dense ionosphere. Even more intriguing are the so-called ocean worlds like Europa or Enceladus, where global saltwater oceans beneath icy crusts could create magnetic fields through tidal friction. If life exists there, it might owe its survival to these secondary magnetic shields, proof that nature finds ways to adapt when the universe tries to strip a world bare. So when we scan the skies for Earth's twin, we're not just looking for rocky planets with water. We're hunting for invisible magnetic signatures, the cosmic armor that lets a planet keep its atmosphere long enough for life to take root. Mars stands as a cautionary tale, a reminder that without magnetism, even the most promising worlds can wither into silence. Out in the cosmic ocean, where stars blink like lighthouses across unimaginable distances, nature has already built the ultimate navigation system, and it's been running flawlessly for millions of years. Pulsars, those rapidly spinning neutron stars with lighthouse-like beams of radiation, could become the GPS of interstellar travel, their precise magnetic pulses acting as celestial breadcrumbs for future spacecraft. Unlike our fragile satellite networks, these cosmic beacons are practically indestructible, emitting rhythmic bursts with the accuracy of atomic clocks. NASA Neutron Star Interior Composition Explorer, or NICER, has already proven this isn't science fiction. Mounted on the International Space Station, this washing machine-sized instrument has demonstrated pulsar-based navigation by timing X-ray flashes from distant neutron stars. The experiment, called Sextant, achieved positioning accuracy within 5 kilometers, all while hurtling through space at 17,500 miles per hour. That's like using stars to navigate across an ocean with the precision of spotting a single streetlight in a city. Here's how it works. Each pulsar has a unique fingerprint, a specific rotation period ranging from milliseconds to seconds, created as its powerful magnetic field channels particles into beams that sweep across space like a cosmic strobe light. By comparing arrival times of pulses from multiple pulsars, a spacecraft could triangulate its position anywhere in the galaxy, much like sailors once used stars to navigate Earth's oceans. The key advantage: unlike Earth-based systems that weaken with distance, pulsar signals remain strong across light years, their stability unaffected by planetary motion or human interference. Imagine a probe bound for Alpha Centauri, its onboard computer storing a pulsar map like an ancient mariner's star chart. As it journeys through interstellar space, it would listen for the telltale ticks of these cosmic metronomes, adjusting course by the infinitesimal delays in pulse arrivals. Millisecond pulsars, those spinning hundreds of times per second, would offer the finest precision, their rapid flashes acting like the ticking hands of a galactic clock. The implications are staggering. While current deep space navigation relies on radio signals from Earth that take hours to reach outer planets, a pulsar-based system would grant spacecraft full autonomy. Colonies on Mars or mining operations in the asteroid belt could maintain their own positioning without waiting for sluggish signals from home. Even more remarkably, this system would work in the farthest reaches of the galaxy, where no human-made signal could ever reach. But pulsar navigation isn't just about practicality, it's also a poetic full circle. Long before GPS satellites, our ancestors navigated by the stars. Now, we might return to that ancient wisdom on an interstellar scale, using the universe's own rhythms to guide our way through the void. The same magnetic phenomena that power these cosmic lighthouses could one day become the street signs of the galaxy, pointing the way to humanity's future among the stars. Long before the first stars flickered to life, before galaxies spiraled into existence, the newborn universe hummed with a different kind of energy, raw, untamed magnetism woven into the fabric of space itself. These primordial fields weren't born from churning stellar cores or spinning black holes. They emerged in the first microseconds after the Big Bang, when the cosmos was a seething ocean of quark-gluon plasma, a state of matter so extreme that even protons and neutrons hadn't yet formed. Picture the universe as a blistering soup of fundamental particles, each carrying an electric charge, their frenetic motion generating magnetic turbulence on scales we can barely comprehend. Recent experiments at the relativistic heavy ion collider have recreated slivers of this primordial plasma by smashing gold nuclei together at nearly light speed. The resulting fireballs, tiny echoes of the early universe, reveal something startling. Magnetic fields in these conditions can reach strengths of 10 to the 18th power Gauss, a number so large it dwarfs even the most powerful magnets in neutron stars. And if these fields existed fleetingly in lab experiments, imagine their cosmic counterparts stretching across the entire infant universe, imprinting their influence on everything that followed. Here's where it gets truly fascinating. These primordial fields didn't just vanish when the universe cooled. Like cosmic fossils, they may have persisted, woven into the first clouds of hydrogen gas that collapsed to form galaxies. Computer simulations show how weak seed fields, perhaps just a trillionth of Earth's magnetic strength, could have been amplified by the turbulent motions of early star formation, like invisible threads pulled taut by gravity's loom. Some astrophysicists speculate that the vast magnetic structures we see in galaxies today, those sprawling interstellar webs, might trace their lineage back to these primordial seeds. But the implications run even deeper. Primordial magnetism could solve one of cosmology's enduring puzzles: why the universe's large-scale structure isn't perfectly smooth. Tiny magnetic fluctuations in the early plasma might have acted like cosmic cookie cutters, nudging matter into denser clumps that became the gravitational wells for future galaxies. It's a humbling thought. The same forces that guide compass needles on Earth might have orchestrated the universe's first grand structures, their influence echoing across 13.8 billion years of cosmic evolution. And the clues keep mounting. The cosmic microwave background, that afterglow of the Big Bang, shows faint hints of polarized light patterns that could bear the fingerprints of these ancient fields. Meanwhile, observations of some of the universe's most distant galaxies reveal magnetic signatures in places theory says shouldn't have had time to generate them naturally. Could these be the last whispers of magnetism's primal origin story? What's clear is this: magnetism isn't just a feature of the universe, it might be one of its foundational pillars, as essential to cosmic architecture as gravity itself. From quark-gluon plasma to galactic superclusters, the invisible hand of magnetism has shaped reality at every scale, a silent architect working in the shadows since the very first moments of time. Deep in the voids between galaxies, particles scream through space at nearly light-speed cosmic rays, the universe's most energetic shrapnel. Some carry energy so extreme, a single proton can hit with the force of a fastball. But here's the cosmic detective story. By the time these particles reach Earth, their original trajectories are hopelessly scrambled, their sources hidden behind a galactic maze of magnetic mirrors. The Milky Way's invisible magnetic web acts like a hall of mirrors for these charged projectiles, bending their paths so severely that tracing them back to their birthplaces, supernova remnants, black hole jets, or even more exotic phenomena becomes nearly impossible. This magnetic deflection creates one of astrophysics' greatest puzzles, the cosmic ray (NE). Plot the energy distribution of these particles on a graph, and at around 1 quadrillion electron volts, the spectrum suddenly bends, like a hiker encountering an unexpected cliff. Below this energy, cosmic rays are relatively abundant. Above it, they become exponentially rarer. For decades, scientists assumed this NE marked the upper limit of what our galaxy's magnetic fields could contain. That beyond this point, particles had enough energy to punch through the Milky Way's magnetic barriers and escape into intergalactic space. But newer observations complicate that picture. The Hawk Gamma Ray Observatory in Mexico has mapped cosmic rays slamming into Earth's atmosphere, revealing something startling. Even particles far beyond the NE's energy still carry signatures of galactic confinement. This suggests the Milky Way's magnetic fields aren't just a cage, they're an accelerator. As protons and heavier nuclei spiral along these twisted field lines, they can gain energy through a process called second-order Fermi acceleration, bouncing off magnetic irregularities like pinballs gaining speed with each collision. The NE might not be an escape threshold, but rather a signpost of where this acceleration mechanism maxes out. Yet the plot thickens when you consider composition. Iron nuclei at the NE's energy behave differently than protons. They bend less in magnetic fields due to their higher charge, offering clues about their journey. Some models suggest these heavy cosmic rays might originate in the turbulent regions around giant molecular clouds, where magnetic fields are strong enough to act as particle traps. Others point to runaway stars, their bow shocks creating natural particle accelerators. But without the ability to trace their paths directly, it's like reconstructing a crime scene where every clue has been tossed in a hurricane. What's clear is this: the Milky Way's magnetic fields don't just shield us from cosmic rays, they reshape our entire understanding of high-energy astrophysics. Every particle that strikes our atmosphere has danced to the tune of these invisible forces, its energy and direction rewritten by magnetic hands. Until we decode their labyrinthine influence, the universe's most powerful particle accelerators will remain hidden in plain sight, their secrets scattered across light years of magnetized space. The Sun isn't the steady, unchanging orb it appears to be from Earth. It pulses with hidden rhythms, governed by an invisible clockwork of magnetic forces. Every 11 years, our star undergoes a dramatic transformation, its surface erupting with sunspots, flares, and coronal mass ejections before settling back into relative calm. This solar cycle isn't just a curiosity. It's the heartbeat of a vast magnetic dynamo, a process deep within the sun where plasma currents twist and stretch magnetic fields like taffy, building up energy until it snaps back in a cosmic reset. Sunspots, those dark blemishes on the sun's face, are the most visible signs of this cycle. They're not just random spots, they're knots of intense magnetism, regions where the sun's field lines pierce through the surface, suppressing convection and cooling the area enough to appear darker against the surrounding inferno. During solar maximum, these spots multiply, clustering near the equator like storm cells on a weather map. But as the cycle progresses, they migrate toward the poles, eventually canceling each other out as opposite magnetic polarities meet and annihilate. It's a self-regulating system, a celestial dance where magnetism builds, breaks, and rebuilds in an endless loop. The consequences of this cycle ripple across the solar system. Solar maximum brings heightened auroras, radio blackouts, and increased radiation hazards for astronauts. But history shows us what happens when the rhythm falters. Between 1645 and 1715, during the Maunder minimum, sunspots virtually disappeared for 70 years, a solar hibernation that coincided with the coldest stretch of the Little Ice Age. Temperatures in Europe plummeted, the Thames froze solid, and glaciers advanced over alpine villages. While the exact link between solar activity and climate remains debated, the correlation is striking. With fewer sunspots, the sun's total irradiance dipped slightly, but more importantly, its magnetic shield weakened, allowing more galactic cosmic rays to reach Earth. Some scientists theorize these high-energy particles seed low-altitude clouds, amplifying cooling effects, a hypothesis supported by modern satellite data showing cloud cover variations with cosmic ray flux. Today, as we enter solar cycle 25, researchers are piecing together the sun's magnetic puzzle with unprecedented precision. NAS, a solar dynamics observatory, captures every twist and kink in the sun's field lines, while the Parker Solar Probe braves million-degree heat to sample the solar wind directly. What they've found is a dynamo far more chaotic than early models suggested, a turbulent mess of plasma flows where magnetic fields are stretched, folded, and shredded like paper in a hurricane. The implications extend beyond weather and auroras. Understanding these cycles could help predict space weather events capable of frying satellites or knocking out power grids. It might even shed light on the habitability of exoplanets orbiting variable stars, where magnetic activity could mean the difference between a temperate world and a lifeless rock. The sun's 11-year pulse isn't just a quirk of our star, it's a masterclass in how magnetism shapes planetary destinies, a reminder that even the mightiest forces in the universe dance to the tune of invisible fields. Beneath Europa's icy crust, in an ocean darker than the deepest trenches of Earth, life might be clinging to existence not with sunlight but with magnetism. This Jovian moon's global saltwater sea, kept liquid by tidal heating, is one of the solar system's most promising candidates for extraterrestrial life. But what truly sets Europa apart isn't just its water. It's the way Jupiter's monstrous magnetic field transforms that ocean into a potential cradle for biology. Charged particles, accelerated to brutal energies by Jupiter's magnetosphere, constantly bombard Europa's surface, blasting apart ice molecules to create oxygen and other reactive chemicals. These could seep downward through cracks in the ice, fueling exotic ecosystems where life draws energy not from photosynthesis but from magnetic chemistry. We've seen whispers of how this might work right here on Earth. At hydrothermal vents along mid-ocean ridges, entire communities thrive in crushing darkness, powered by chemosynthesis bacteria converting minerals and sulfur into energy. But on Europa, the recipe could be even stranger. Magnetic fields might induce electric currents in the moon's salty ocean, creating natural batteries at mineral-rich thermal vents. Some extremophile microbes, like the magnetic sensing bacteria found in Earth's deep-sea sediments, could theoretically exploit these currents, aligning themselves along field lines like living compass needles. Others might use the constant bombardment of high-energy particles as an energy source, breaking down oxidants in a process called radiolysis, essentially feeding on radiation the way plants feed on sunlight. The clues are tantalizing. When the Hubble Space Telescope detected plumes of water vapor erupting from Europa's south pole, analysis suggested they contained not just salts, but organic molecules, the building blocks of life. More tellingly, NASA Galileo spacecraft detected disturbances in Jupiter's magnetic field near Europa, hinting at conductive materials moving beneath the ice, perhaps a salty, electrically charged ocean swirling in Jupiter's magnetic embrace. Yet the real marvel lies in the possibilities we haven't even imagined. Life in Europa's depths wouldn't just endure magnetism, it might depend on it. Fields could guide migratory patterns of microscopic organisms, or even influence biochemical reactions in ways unseen on Earth. If future missions like Europa Clipper find evidence of biology there, it would rewrite our understanding of life's requirements, proving that where there's liquid water, an energy source, and a magnetic dance between a moon and its planet, life might find a way to spin gold from chaos. This isn't just about one icy moon. Across the galaxy, similar scenarios could play out on tidally locked exoplanets orbiting red dwarfs, or in the subsurface oceans of Enceladus and Ganymede. Magnetic fields might be the invisible architects of life's resilience, turning radiation into opportunity and chaos into chemistry. So while we search for Earth-like planets bathed in sunlight, we shouldn't overlook the shadow biospheres, where life, armed with nothing but water and magnetism, could be writing its own strange rules of survival. Drifting through the black between stars, the so-called empty space isn't empty at all. It's a sculptor's workshop where magnetic fields mold the raw materials of the cosmos. The interstellar medium, that diffuse mix of gas and dust, might look like random chaos to the naked eye, but zoom in with radio telescopes, and you'll find intricate filaments, threads of material stretched like taffy across light years, their shapes revealing the invisible hands of magnetism at work. Nowhere is this more stunning than in the Orion Molecular Cloud Complex, a star-forming region where the European Space Agency's Planck telescope captured something extraordinary. A map of polarized light showing magnetic field lines threading through the dust like stitches in a cosmic quilt. These filaments aren't just pretty patterns, they're the universe's construction blueprints. As gravity pulls gas and dust together, magnetic fields channel the flow, preventing the material from collapsing into a formless blob. Picture trying to pour sand onto a magnetized surface. The grains align into spiky ridges instead of spreading evenly. On an interstellar scale, this process creates dense ribbons where gravity can eventually ignite new stars, while the surrounding voids remain eerily empty. Without magnetism's guiding touch, star formation would be a messy free-for-all, with no organized structure to nurture stellar birth. Planck's data revealed something even more profound. These fields aren't passive bystanders. They actively resist gravity's pull, propping up some gas clouds like invisible scaffolding. In certain regions of Orion, the field strength measures just a few microgauss, faint compared to Earth's magnet, but enough to shape the destiny of entire stellar nurseries. When turbulent motions within the cloud twist these field lines, they snap back like overstretched rubber bands, releasing energy that heats the surrounding gas and influences how quickly stars can form. It's a delicate balancing act. Too much magnetic pressure and star formation stalls, too little, and the cloud collapses too fast, birthing unstable, short-lived stars. But the real marvel lies in the details. Some filaments glow with synchrotron radiation, their dust grains aligned like countless tiny compass needles, all pointing along the local magnetic field. Others show bizarre helical twists, suggesting places where competing forces have wound the fields into cosmic springs. And in the darkest, coldest cores of these clouds, where temperatures hover just a few degrees above absolute zero, magnetism might be the only thing preventing total gravitational collapse, creating the conditions for future solar systems to emerge. So the next time you gaze at Orion's sword, remember, you're not just seeing stars, you're witnessing the aftermath of an invisible war between gravity and magnetism, a battle that's been raging for millions of years, one that shapes not just how stars are born, but what kinds of planets and maybe even life they'll one day host. The interstellar medium isn't just space. It's a magnetic masterpiece still wet with the brushstrokes of creation. When a star dies in a supernova explosion, most of its energy doesn't escape as light. It flees in the form of ghostly particles called neutrinos, so elusive they can pass through light years of lead without a single collision. But these cosmic ghosts don't travel unchanged. As they race through the tangled magnetic wreckage of the exploding star, something extraordinary happens. They shapeshift. One moment, a neutrino is an electron neutrino. The next, it's morphed into a muon or tau flavor, a quantum magic trick called neutrino oscillation. And in the chaos of a supernova's magnetic maelstrom, these oscillations don't just alter particle identities, they rewrite the entire energy balance of the explosion. The smoking gun for this process came from supernova 1987A, the closest stellar explosion observed in modern times. For 3 fleeting hours, detectors on Earth captured 24 neutrinos from the dying star, but the numbers didn't add up. Theory predicted 10 times more electron neutrinos than were actually detected. The missing particles hadn't vanished, they'd transformed. As the neutrinos plowed through the supernova's ferociously magnetized debris, their quantum flavors oscillated like colors in a spinning top, turning electron neutrinos into other varieties that early detectors couldn't see. Here's why it matters. Neutrinos carry 99% of a supernova's energy output. Their ability to escape the collapsing star dictates how much material gets blown away versus how much collapses into a neutron star or black hole. Magnetic fields turbocharge this process by twisting the neutrino's quantum states. In the supernova's inner core, where densities reach 100 trillion times Earth's atmosphere and magnetic fields hit 10 billion Gauss, neutrinos don't just oscillate, they resonate. Certain magnetic field strengths create flavor transformation hotspots where neutrinos change identity en masse like synchronized swimmers. Computer simulations reveal the cascading effects. When too many electron neutrinos convert to other flavors, the star's core loses a critical pressure source, altering the shockwave's strength. Some models suggest this could explain why 1987A's explosion was slightly fainter than expected. Its magnetic fields may have siphoned energy into invisible neutrino flavors that didn't contribute to the blast. Other studies propose that extreme magnetic oscillations might even trigger asymmetric explosions, launching newborn neutron stars across galaxies like cosmic cannonballs. But the real frontier lies in what we can't yet see. Next-generation detectors like the Deep Underground Neutrino Experiment will catch neutrinos from future supernova across all 3 flavors, letting us reconstruct the magnetic fingerprints hidden in their oscillation patterns. Each transformation encodes information about the fields that guided it, a cosmic cipher waiting to be cracked. So when the next nearby star explodes, its neutrinos won't just bring news of a death. They'll carry encrypted blueprints of the most violent magnetic environments in the universe. And as we learn to read their shape-shifting language, we may finally understand why some supernovas shine bright while others whisper, and how magnetism, the universe's invisible choreographer, directs the dance. Dark matter might be invisible, but its fingerprints could be written in the language of magnetism. Among the most tantalizing possibilities is that this mysterious substance, making up 85% of the universe's matter, interacts with magnetic fields in ways we're only beginning to unravel. One leading hypothesis involves particles called actions, theoretical leftovers from the early universe that could convert into photons in the presence of strong magnetic fields. Picture a galactic halo, a vast, diffuse cloud of dark matter enveloping a galaxy like an invisible cocoon. If actions exist, they might transform into faint radio waves as they pass through the magnetized plasma permeating these halos, leaving behind an electromagnetic whisper we could detect. The experimental hunt for this signal is already underway. Projects like the Action Dark Matter experiment use powerful superconducting magnets to create conditions where actions might reveal themselves. Inside these detectors, magnetic fields thousands of times stronger than Earth's fill a chilled vacuum chamber, acting as a cosmic catalyst. If even a single action oscillates into a microwave photon here, sensitive antennas would catch its signature. While no definitive detection has been made yet, the mere possibility rewrites what we thought we knew about dark matter's relationship with electromagnetism. Traditional models assumed dark matter was completely inert, silent, and unaffected by magnetic forces. But if actions or similar particles interact, even weakly, with these fields, it could open a backdoor to understanding the universe's most elusive substance. There's another twist. Some galaxies show magnetic fields extending far beyond their visible disks, into regions where dark matter dominates. How these fields sustain themselves without obvious plasma currents to generate them remains a puzzle, unless dark matter itself plays a role. Simulations suggest certain dark matter particles could carry tiny electric dipole moments, creating minuscule currents that amplify or distort galactic magnetic fields in unexpected ways. The resulting distortions might explain anomalies like the coherent magnetic fields found in pristine, early galaxies, which shouldn't have had enough time to grow such organized structures through conventional means. What makes these ideas so compelling is their testability. Radio telescopes like the Square Kilometre Array could soon scan the skies for the predicted action photon glow emanating from galaxy clusters. Meanwhile, laboratory experiments are pushing sensitivity to unprecedented levels, probing the parameter space where actions might hide. Every null result narrows the possibilities, inching us closer to either a breakthrough or a paradigm shift. This isn't just about finding particles, it's about rewriting the rules of cosmic influence. If dark matter and magnetism shake hands, even faintly, it would mean the universe's dominant matter isn't entirely dark after all. Its presence might ripple through the very fields that shape stars, galaxies, and perhaps even the conditions for life. And in that faint electromagnetic hum, we could finally hear the voice of the invisible. Even in the perfect void of empty space, where nothingness reigns supreme, magnetic fields can stir up chaos by bending the rules of reality itself. According to quantum mechanics, what we call a vacuum isn't truly empty. It's a seething, bubbling ocean of virtual particles, pairs of electrons and positrons that flicker in and out of existence so fast we can't detect them directly. But under the grip of an ultra-strong magnetic field, even these ghostly particles can't escape notice. The field twists the vacuum like a cosmic ringer, polarizing virtual pairs until space-time itself behaves differently. This bizarre phenomenon, predicted by physicist Julian Schwinger back in 1951, suggests that in the presence of overwhelming magnetic force, the vacuum isn't just a passive backdrop. It becomes an active player in shaping the universe's behavior. The math behind this is staggering. At field strengths approaching 10 to the 18th power Gauss, conditions found near magnetars or in the first microseconds after the Big Bang, something extraordinary happens. The energy required to rip a virtual electron-positron pair apart becomes so low that the vacuum spontaneously spawns real particles, no longer virtual. This is the Schwinger effect, a magnetic field so intense it literally conjures matter from nothingness, like plucking coins from thin air. In lab experiments, scientists have glimpsed hints of this using ultra-powerful lasers to mimic the necessary conditions, observing how particle pairs emerge where there should be only void. But out in the cosmos, nature has already built furnaces where this process runs wild. The implications rewrite our understanding of space itself. Normally, we think of the vacuum as having set properties, a constant speed of light, fixed electrical permeability. But in these extreme magnetic environments, those rules bend. Light might travel slightly slower through a magnetized vacuum, its path curved by the polarized quantum foam. Even more mind-bending is the idea that these effects could leave cosmological fingerprints. Some theorists suggest that primordial magnetic fields, stretching across the universe since its infancy, might have subtly altered the cosmic microwave background's polarization patterns through vacuum polarization, an echo of quantum weirdness imprinted on the oldest light in existence. What makes this truly revolutionary is how it blurs the line between nothing and something. The vacuum isn't just empty space waiting to be filled. It's a dynamic medium that responds to magnetism like an instrument responding to a bow. And in places where fields reach their most extreme black hole horizons, quark stars, or the aftermath of colliding neutron stars, this quantum dance might hold the key to phenomena we've yet to explain. Energy could emerge spontaneously, particles might materialize without obvious sources, and the very fabric of spacetime could ripple in ways Einstein never anticipated. So the next time you think of empty space, remember, it's only empty until a magnetic field shows up. Then, like a magician's hat tipped upside down, the universe reveals it was never truly empty at all, just hiding its secrets in plain sight. The universe isn't just a random scattering of galaxies, it's an intricate web, a vast cosmic tapestry where threads of dark matter and gas weave together in patterns spanning billions of light years. And now, thanks to groundbreaking observations from the LOFAR radio telescope, we've discovered something extraordinary. Those filaments aren't just shaped by gravity, they're threaded with magnetic fields aligned to the web itself. It's as if the universe's largest structures are embroidered with invisible magnetic stitching, a hidden force guiding the architecture of everything we see. LOFAR-sensitive antennas have mapped these fields in unprecedented detail, revealing how they trace the cosmic web's faint filaments like glowing ink on dark parchment. The key lies in synchrotron radiation, the faint radio glow emitted when charged particles spiral around magnetic field lines. By analyzing this signal from distant galaxy clusters, scientists found something startling. The fields don't run haphazardly. They're preferentially aligned along the web's densest filaments, as though magnetism and gravity are dancing to the same cosmic rhythm. One of the clearest examples lies in the so-called cosmic highway between the galaxy clusters Abell 399 and Abell 401. Stretching 10 million light-years, this bridge of hot gas should be turbulent, its magnetic fields tangled like spaghetti. Instead, LOFAR detected a coherent field running parallel to the filament, as straight as a laser beam. The implication: magnetic forces might be smoothing the flow of matter along these intergalactic thoroughfares, acting like cosmic traffic cops directing the movement of galaxies. But how do fields this organized exist in what should be chaos? Simulations suggest the answer lies in the universe's infancy. Primordial magnetic seeds, born in the Big Bang's aftermath, could have been stretched and amplified as the cosmic web formed, their lines pulled taut like rubber bands as matter flowed into filaments. Alternatively, the fields might be self-perpetuating galactic winds and active black holes injecting plasma into the voids, where turbulence twists and strengthens magnetism over eons. Either way, the result is the same, a universe where magnetism isn't just present in the voids, it's shaping them. The consequences ripple across cosmology. If magnetic fields thread the cosmic web, they could influence how galaxies form and evolve within these structures. Gas falling into filaments might be channeled more efficiently, altering star formation rates. The fields might even solve the mystery of why some galaxy clusters appear to spin coherently despite being separated by vast distances, their rotation synchronized by magnetic bridges we're only now learning to see. What's truly humbling is the scale. These fields are unimaginably weak, 1,000,000 times fainter than Earth's, yet they span volumes so large they defy comprehension. They're the universe's quiet conductors, orchestrating the flow of matter not with brute force, but with patient, invisible guidance. And as LOFAR and next-generation telescopes like the Square Kilometre Array probe deeper, we may find that magnetism's role in the cosmic web isn't just supportive, it's foundational, a silent partner to gravity in building the universe's grand design. Among the embers of dead stars, white dwarfs usually fade quietly into the cosmic background but sprinkle in an ultra-strong magnetic field, and these stellar retirees become some of the universe's most bizarre spectacles. Take GRW plus 70 degrees 8247, a white dwarf so magnetized its field doesn't just influence its surroundings, it warps the very light escaping its surface. Clocking in at around 300 million Gauss, this star's magnetic grip is powerful enough to split spectral lines like a prism on steroids, a phenomenon so extreme it left astronomers baffled for decades. Here's how it works. Normally, when atoms in a star's atmosphere absorb and re-emit light, they produce distinct dark or bright lines in the spectrum, a chemical fingerprint revealing which elements are present. But under GRW plus 70 degrees 8247's monstrous field, something extraordinary happens. The field's strength alters the quantum energy levels of electrons in these atoms, a process called the Zeeman effect on steroids. Imagine a pianist hitting a single key only to have the note fracture into a dissonant chord. That's what happens to light here. Single spectral lines split into multiple components, their wavelengths stretched and squeezed by magnetic forces until the star's spectrum looks less like a barcode and more like a shattered mirror. What makes this star particularly puzzling isn't just the field's strength, it's how it got there in the first place. Most white dwarfs are born from sun-like stars that shed their outer layers peacefully, leaving behind cores that should have relatively weak magnetism. Yet GRW plus 70 degrees 8247 defies the odds, packing a field thousands of times stronger than typical white dwarfs. One theory suggests mergers might be to blame, two white dwarfs colliding and merging their magnetic fields in a violent embrace. Another posits that these ultra-magnetized dwarfs could be the fossilized cores of stars that were unusually magnetic to begin with, their fields compressed and amplified as the star collapsed. The practical effects of such extreme magnetism are mind-bending. On a planet orbiting GRW plus 70 degrees 8247, compass needles wouldn't just point north, they'd snap in half. Auroras would cover the entire sky, not just the poles, as charged particles spiral uncontrollably along magnetic field lines, and any electronic equipment would fry instantly, overwhelmed by the relentless electromagnetic forces. Yet these magnetic oddities might be more than just cosmic curiosities. Some researchers speculate that highly magnetized white dwarfs could be the source of certain unexplained transient events in the universe, brief flashes of energy that appear and vanish before we can pinpoint their origin. Others suggest their intense fields might influence the evolution of surrounding planetary systems, shredding any surviving asteroids or comets into charged dust. So while GRW plus 70 degrees 8247 might seem like an outlier, it's a reminder that even in death, stars can defy expectations. These magnetic monsters challenge our understanding of stellar evolution, proving that the universe always keeps a few wild cards up its sleeve, white dwarfs that didn't just retire quietly but went out with a magnetic bang. What if the key to unlocking time travel has been hiding in plain sight, not in exotic matter or cosmic strings, but in the magnetic fields that saturate the universe? The idea isn't as far-fetched as it sounds. Einstein's general relativity allows for the existence of wormholes, hypothetical tunnels through space-time known as Einstein-Rosen bridges. But there's a catch. These cosmic shortcuts are notoriously unstable, snapping shut the instant anything tries to pass through. That's where magnetism might rewrite the rules. Theoretical physicists have proposed that ultra-strong magnetic fields could act like cosmic scaffolding, propping open a wormhole's throat long enough for information, or even matter, to traverse it. The math behind this is as elegant as it is mind-bending. Magnetic fields, when intense enough, can warp space-time in ways that counteract a wormhole's natural tendency to collapse. Picture a black hole's event horizon, a point of no return where gravity's grip is absolute. Now imagine threading that horizon with magnetic field lines so powerful they create a repulsive force, balancing the crushing weight of gravity like two cosmic sumo wrestlers locked in a stalemate. Under these conditions, calculations suggest a wormhole could remain traversable, at least momentarily. The magnetic field wouldn't just hold the door open, it would stabilize the chaotic quantum foam at the wormhole's core, preventing the violent fluctuations that normally tear these spacetime tunnels apart. But where in the universe could such conditions exist? Magnetars, those ultramagnetic neutron stars, are prime candidates. With fields measuring a quadrillion times Earth's, their surroundings are already laboratories for extreme physics. Some models suggest that if two magnetars with oppositely aligned fields were to collide, the resulting magnetic turbulence could twist spacetime into a temporary wormhole. Even more speculative is the idea that primordial black holes, leftover relics from the Big Bang, might harbor magnetic fields strong enough to sustain microscopic wormholes in the quantum foam, flickering in and out of existence like soap bubbles in a cosmic breeze. The implications are staggering. If magnetic fields can stabilize wormholes even briefly, they might enable a form of time telegraphy, sending messages backward in time encoded in polarized photons. Experiments with quantum entanglement have already shown that magnetic fields can influence particle behavior instantaneously across distances, hinting at a deeper connection between magnetism and the fabric of spacetime itself. Of course, the energy requirements are astronomical, and the stability windows would likely be measured in fractions of a second. But in a universe where magnetic fields already perform seemingly impossible feats, from birthing stars to shaping galaxies, the line between science fiction and science fact has always been thinner than we think. So while we're far from building a time machine, the cosmic playground of magnetism offers something equally valuable. A reminder that the universe's secrets often hide in the interplay between its most fundamental forces. Wormholes may remain theoretical for now, but their potential link to magnetic fields suggests that if time travel is ever possible, it won't be through brute force or exotic technology. It'll be by harnessing the invisible threads that already stitch the cosmos together. Plasma, often called the fourth state of matter, dominates the visible universe, yet its behavior defies intuition. Unlike solids, liquids, or gases, this superheated soup of charged particles dances to the tune of an invisible conductor, magnetism. The science of magnetohydrodynamics, or MHD, reveals how magnetic fields choreograph plasma's chaotic motions, shaping everything from the swirling disks feeding black holes to the stellar winds that sculpt entire star systems. Take accretion disks, those luminous whirlpools of gas spiraling into cosmic predators like black holes and neutron stars. Without magnetic fields, these disks would behave like simple whirlpools with material flowing smoothly inward. But reality is far more dynamic. Observations from telescopes like Chandra and Alma show these disks are riddled with turbulence, jets, and bizarre structures resembling cosmic hurricanes. The culprit, magnetic fields twisted to their breaking point. As plasma orbits the central object, its charged particles drag magnetic field lines like strands of spaghetti wound around a fork. This creates opposing forces. The disk's rotation tries to wind the fields tighter, while magnetic tension fights back, eventually snapping and reconnecting in explosive bursts. The result is a self-regulating conveyor belt. Magnetic turbulence heats the plasma, preventing it from collapsing too quickly, while also funneling material into jets that shoot outward at relativistic speeds. Stellar winds tell a similar story. Our own sun exhales a breeze of charged particles, but in massive stars, these winds become gale force. The key difference lies in magnetism. Stars with strong magnetic fields, like the young, rapidly rotating T-Tauri stars, channel their winds into rigid columns aligned with magnetic poles. These collimated outflows can extend for light years, plowing through interstellar clouds and triggering star formation like cosmic dominoes. Meanwhile, red giants exhibit a stranger phenomenon. Their weak surface fields become entangled in the wind itself, creating a fractal web of magnetic bubbles that slow the wind's escape, altering how these stars shed mass in their final years. The equations governing this behavior, Navier-Stokes meets Maxwell's electromagnetism, are so complex they challenge even supercomputers. Yet simulations like those from the Princeton Plasma Physics Laboratory reveal stunning details. Magnetic fields don't just guide plasma, they can self-organize. In some accretion disks, fields spontaneously form coherent structures called magneto-rotational vortices, stable whirlpools within whirlpools that act as particle traps, potentially seeding planet formation. Elsewhere, magnetic reconnection, events those violent rearrangements of field lines convert stored magnetic energy into blistering heat, explaining why the sun's corona is millions of degrees hotter than its surface. What's truly humbling is how universal these principles are. The same MHD processes that shape star formation also govern the behavior of fusion reactors on Earth, where controlling plasma with magnetic fields could unlock limitless clean energy. From the smallest laboratory tokamak to the largest active galactic nucleus, plasma and magnetism are inseparable partners. One a fiery, chaotic substance, the other an invisible hand bringing order to the chaos. The next time you see an image of a quasar's jet or hear about a solar storm, remember, you're witnessing magnetohydrodynamics in action, the universe's way of writing its grandest stories in the language of charged particles and unseen fields. When neutron stars collide, they don't just send ripples through space-time, they scream in a language of twisted magnetism. Gravitational wave detectors like LIGO have given us front-row seats to these cosmic crashes, listening for the faint whispers of warped space. But what if some of those whispers are lies? Hidden in the data could be magnetic fingerprints, distortions warping the signals like a funhouse mirror, making these collisions seem stranger or even more common than they really are. The chaos starts deep inside the merging stars. Neutron stars are nature's most powerful magnets, with fields trillions of times stronger than Earth's. As two of these magnetized monsters spiral toward each other, their fields don't just collide, they tangle, snap, and reconnect in a frenzy of electromagnetic violence. Simulations show this magnetic mayhem can actually torque the star's exteriors, altering how mass distributes during the final moments before impact. Since gravitational waves encode information about the merging objects' shapes and masses, these magnetic distortions could trick LIGO into misreading the star's true properties. Imagine trying to identify a bell by its ring, but someone keeps nudging the clapper. The sound changes, and so does your guess. The smoking gun might lie in the chirp, the rising pitch of gravitational waves as neutron stars close in. Normally, this signal follows a predictable pattern based on mass and distance, but magnetically driven turbulence could inject erratic wobbles like a record skipping mid-play. During the landmark GW event in 2017, some researchers noted faint anomalies in the signal's tail, tiny fluctuations that didn't match clean models. While most blamed imperfect simulations, a daring few suggested magnetism as the phantom culprit. Even more intriguing is what happens post-merger. If the collision forms a hypermassive neutron star, a fleeting, unstable remnant, its ludicrously amplified magnetic field could literally shake space-time. Charged particles whipped into vortices by these fields would emit their own secondary gravitational ripples, layering noise atop the main signal. Future detectors like the Einstein telescope with 10 times LIGO sensitivity might catch these magnetic echoes, revealing whether what we've been hearing all along is a duet or a distorted solo. The stakes go beyond mere accuracy. Misreading these signals could skew our senses of neutron stars, fooling us into thinking some mergers involve stranger objects like quark stars or primordial black holes. It might even affect how we measure the universe's expansion rate, since gravitational waves serve as cosmic yardsticks. Magnetism, the universe's silent ventriloquist, might be throwing its voice into the data, and until we learn to decode its interference, some collisions will remain cosmic mysteries dressed up as revelations. Jupiter and its volcanic moon Io offer a blueprint for finding hidden worlds light years away. Their magnetic tango, where Io's eruptions fill Jupiter's magnetosphere with charged particles, creates a detectable electromagnetic signature. Now, astronomers are turning this local phenomenon into a universal exomoon hunting tool. The principle is simple. If a moon orbits within an exoplanet's magnetic field, its volcanic activity, or even just its conductive subsurface ocean, should generate currents producing faint but measurable radio waves. Take the exoplanet candidate system Kepler 1625. When researchers noticed unusual dips in starlight that didn't quite match a planet's transit pattern, they proposed a Neptune-sized world with a moon half Earth's mass. But how to confirm it? Enter magnetism. If that moon is geologically active like Io, or harbors a salty ocean like Europa, its interaction with the planet's magnetic field should emit low-frequency radio bursts. Telescopes like LOFAR are already scanning for these whispers, tuning into frequencies between 5 and 30 megahertz where such signals might hide. The real prize: ice giants with water-rich moons. Imagine a scaled-up version of Uranus, a pale blue exoplanet with a tilted, chaotic magnetic field. A moon skimming its magnetosphere could induce shimmering auroral rings in the planet's atmosphere, visible as subtle flickers in infrared spectra. Even more telling would be periodic radio pulses timed to the moon's orbit, a dead giveaway of electromagnetic interaction. Of course, challenges abound. Stellar activity can drown out these faint signals, and not all moons will be as vocal as Io. But next-generation instruments like the Square Kilometre Array will turn up the volume on these cosmic conversations, listening for the unique static of exomoons shaping their planet's magnetic fields. Success would mean more than ticking moons off a list. It could reveal which distant worlds have the magnetic chemistry to nurture life under icy shells. So while we stare at pinpricks of light, the real clues might come from the invisible. The static hiss of a moon's electromagnetic scream across the void, a siren song waiting to be decoded. Could the blueprint for life have been written in the language of magnetism, hidden in the swirling chaos of stellar nurseries where newborn stars illuminate vast clouds of gas and dust? An extraordinary molecular preference might hold the key. Chiral molecules, those that come in left or right-handed versions, like the double helix of DNA, are essential to life as we know it. Yet how these asymmetrical structures emerged from a chaotic early universe has puzzled scientists for decades. The answer could lie in the faint but pervasive magnetic fields threading through the nebulae where stars and potentially planets are born. Take amino acids, the building blocks of proteins. In lab experiments, when subjected to polarized light, a proxy for the influence of magnetic fields, these molecules form more of one-handedness than the other. Now scale that up to a nebula. As dust grains coated with simple organic compounds drift through magnetized gas clouds, their electrons align with the field, subtly favoring the formation of one molecular orientation over its mirror image. Over millions of years, this tiny bias could snowball, enriching entire regions of space with a preferred chirality, like a cosmic assembly line pre-configuring life's ingredients before planets even form. The Rosetta mission provided a tantalizing clue when it detected the amino acid glycine on Comet 67P. Even more intriguing, the samples showed slight chiral excess, hinting that the asymmetry might not be unique to Earth. If similar imbalances exist in other star-forming regions, it would suggest magnetism acted as a universal sculptor, nudging chemistry toward complexity long before the first cell membranes formed. But how do we bridge the gap between these microscopic preferences and the leap to life? Magnetized nebulae might accelerate the process. In regions where fields are strongest, polarized ultraviolet light common around young, energetic stars could further amplify the chirality of organic molecules. Simulations show that in such environments, even a 1% initial bias can grow exponentially as material cycles through protoplanetary disks, eventually seeding fledgling worlds with a head start toward biologically relevant chemistry. The implications are profound. If magnetic fields set the stage for life's molecular foundations, then planets forming in highly magnetized nebulae could have a greater likelihood of fostering biology. It might also explain why Earth's amino acids skew left-handed while our sugars prefer right-handed configurations, a legacy written in the magnetic whispers of our solar system's birth cloud. So the next time you gaze at the stars, consider this. The same invisible forces that shape galaxies and ignite suns might also have gently tilted the cosmic scales, setting in motion the delicate asymmetry that makes life possible. Far from random, our existence could be the result of magnetism's subtle, persistent hand, a silent architect of complexity in an otherwise indifferent universe. When two neutron stars spiral toward their doom, their death throes unleash a cosmic spectacle brighter than entire galaxies, but the real show starts when magnetism takes center stage. These collisions, called kilonovae, are the universe's ultimate alchemists, forging heavy elements like gold and platinum in their violent embrace. Yet without the invisible hand of magnetic fields shaping the chaos, these treasures might never escape into the cosmos. Picture the final moments before impact, two city-sized stellar corpses, each denser than an atomic nucleus, whip around each other hundreds of times per second. Their ridiculous magnetic fields, some 1 trillion times stronger than Earth's, twist into braided coils as they merge. This isn't just a collision, it's an electromagnetic hurricane. Simulations reveal that when the stars finally touch, these wound-up magnetic springs snap, launching jets of neutron-rich material at nearly light speed. The resulting shockwaves superheat the surrounding debris, turning it into a furnace where rapid neutron capture, or the R process, occurs. This is how we get gold-heavy atomic nuclei gorging on free neutrons like patrons at an all-you-can-eat buffet, then decaying into precious metals. But here's where magnetism flips the script. Normally, this neutron-rich soup would expand too quickly for heavy elements to form. Magnetic fields solve this by acting like cosmic baffles, slowing the expansion just enough to let the R process run its course. The proof: observations of the historic GW event in 2017. The kilonova's light curve, its fading glow over days matched models where magnetic turbulence extended the cooking time for heavy elements. Spectra later revealed telltale fingerprints of strontium and gold in the debris, confirming magnetism's starring role. The aftermath is even more astonishing. Those magnetically launched jets don't just taper off, they spiral into helix-shaped plumes, their paths etched by lingering magnetic turbulence. This explains why some kilonovae shine brighter in certain directions, like celestial lighthouses. In fact, without these structured outflows, much of the freshly minted gold might fall back into the black hole or neutron star left behind. Instead, magnetism ensures a generous cosmic dispersal, sprinkling heavy elements across interstellar space like a farmer casting seeds. So the next time you admire a gold ring or a platinum necklace, remember, you're holding stardust forged in a magnetic maelstrom, a keepsake from one of the universe's most violent and beautifully orchestrated fireworks displays. The same forces that guide compass needles on Earth once sculpted the very elements that make up our bodies and our world, proving that magnetism isn't just a background player in cosmic evolution. It's the invisible jeweler crafting the universe's most precious gifts. Somewhere in the afterglow of the Big Bang, hidden in the universe's oldest light, lies a controversial fingerprint, one that could rewrite our understanding of cosmic origins. The cosmic microwave background, or CMB, that faint microwave whisper from the infant universe, isn't just a uniform glow. Its polarization patterns, subtle swirls and curls in the light's orientation hold clues to the universe's first moments. But what if some of those patterns weren't sculpted by gravity alone? What if primordial magnetic fields woven into spacetime during cosmic inflation left their own indelible marks? This isn't just speculation. The BICEP and Keck array telescopes perched in the thin air of the South Pole have spent over a decade hunting for these elusive signals. Their target, a specific polarization pattern called B modes, which could betray the influence of magnetism during inflation, that explosive expansion of space in the universe's first trillionth of a second. The reasoning is elegant. If magnetic fields existed before the first stars, their energy would have stretched and twisted spacetime itself, imprinting distinctive curls on the CMB's polarization like fingerprints on glass. But the data tells a complicated story. Early BICEP-2 results in 2014 sent shockwaves through cosmology, hinting at primordial B modes that might have been magnetic in origin until follow-up studies revealed galactic dust had muddied the signal. The Keck array's more sensitive measurements then tighten the constraints, showing that if primordial magnetism exists, it's far weaker than some theories predicted. Yet the door isn't fully closed. Subtle anomalies linger in the CMB's largest scale patterns, hints of asymmetry and unexpected alignments that standard inflation models struggle to explain. Enter the magnetic wildcards. Some theorists propose that exotic physics during inflation, phase transitions in the early universe's vacuum, or collisions between space-time bubbles could have spawned weak but pervasive magnetic fields. These wouldn't be the familiar fields we know today, generated by moving charges. Instead, they'd be relics of a more fundamental symmetry breaking, frozen into the fabric of space as the universe cooled. If such fields existed, even at a puny strength of a billionth of a Tesla, their cumulative effect over inflation's exponential expansion could have left detectable scars. The stakes are high. If primordial magnetism is confirmed, it would mean the universe's magnetic tapestry isn't just a later addition. It's part of the foundation, as fundamental as gravity or dark matter. It could reshape our understanding of cosmic inflation, suggesting that electromagnetism and spacetime were entangled from the very first moments. But if further observations rule it out entirely, we're left with a puzzle. How did the first magnetic fields arise so quickly after the Big Bang? And why do even the most distant galaxies show organized magnetism when there shouldn't have been time for it to develop? For now, the CMB keeps its secrets close. Next-generation experiments like CMB S4, with detectors 10 times more sensitive, will scan the sky for the faintest magnetic whispers. Whether they find them or not, the search itself reveals something profound. The universe's oldest light isn't just a snapshot of the past. It's a mirror reflecting the invisible forces that might have shaped everything we see and everything we are. Dark energy might be the universe's greatest mystery, an invisible force ripping space apart faster every second. But what if magnetism holds a clue to its true nature? The Standard Model pins cosmic acceleration on a cosmological constant, lambda, in the lambdactum framework, representing dark energy as a smooth, unchanging background. Yet some theorists are chasing a wilder idea: phantom fields, where magnetic energy doesn't just influence matter, it warps the very fabric of expansion itself. Picture a universe where dark energy isn't passive but dynamic, threaded with exotic magnetic fields that repel rather than attract. These wouldn't be ordinary magnetism, no fridge magnets or compass needles here. Instead, they'd arise from hypothetical particles coupling to spacetime in ways that flip gravity's script. In certain string theory models, so-called action-like fields could generate cosmic-scale magnetism capable of negative pressure, stretching space faster than lambda alone predicts. The math gets dizzying. These fields would strengthen as the universe expands, their energy density climbing rather than diluting, like a spring coiling tighter instead of unwinding. Observational clues already hint at something amiss. The Hubble tension, the stubborn mismatch between early and late universe expansion measurements, might find an explanation if phantom magnetism tweaked the acceleration rate over cosmic time. Even more provocative are anomalies in large-scale structure. Galaxy surveys reveal unexpected voids and filaments too vast for standard lambdactum, as if invisible magnetic fingers were sculpting the cosmos extra fast. Critics argue these ideas stretch plausibility, but nature has a habit of outdoing imagination. If verified, magnetized dark energy wouldn't just rewrite textbooks, it'd redefine reality's rulebook. The universe's acceleration might not be a fixed decree, but a dance between visible and hidden forces, where magnetism, often seen as local and secondary, emerges as a cosmic conductor tuning the tempo of existence itself. Deep in the quantum foam of spacetime, where the laws of physics blur into uncertainty, the universe may harbor its most elusive predators, tiny primordial black holes, remnants of the Big Bang's violent birth. These microscopic monsters, some no larger than an atom yet packing the mass of a mountain, could be the ultimate testing ground for the greatest unsolved puzzle in physics, quantum gravity. And here's the cosmic twist: their magnetic fingerprints might be the key to spotting them. Most black holes we know are born from collapsing stars, but primordial black holes are different. They're thought to have formed in the first chaotic microseconds of the universe, when extreme density fluctuations created gravitational pits so deep even light couldn't escape. What makes them special isn't just their size, it's their potential to warp the quantum realm. According to Hawking radiation, these tiny black holes should evaporate explosively, their final moments releasing a burst of particles and energy. But if quantum gravity alters this process, the telltale signs could be written in magnetic signatures. Here's why: as a primordial black hole evaporates, the particles it emits, electrons, positrons, and other charged particles, would spiral along the black hole's magnetic field lines. Even a weak field, imprinted during the black hole's creation, would polarize this radiation, creating distinct patterns in the particles' trajectories. Imagine a cosmic firework where the sparks don't spray randomly but align like iron filings around a magnet. Advanced detectors like the Cherenkov telescope array are now scanning the skies for these polarized gamma-ray bursts, hunting for the fleeting flashes that could betray a quantum black hole's demise. But the real magic happens when quantum gravity enters the picture. Some theories suggest that at the tiniest scales, spacetime itself becomes granular, like a digital image zoomed in too far. If true, a primordial black hole's magnetic field might stutter as it interacts with this frothy spacetime, imprinting subtle hiccups in its evaporation signal. These anomalies, deviations from Hawking's original predictions, could be smoking gun evidence of quantum gravity at work. The implications are staggering. Detecting these magnetic whispers wouldn't just confirm primordial black holes existed, would open a direct window into the quantum structure of gravity itself. Are space and time fundamentally pixelated? Does gravity merge with the other forces at these extreme scales? A single polarized gamma-ray flash could hold the answers. And the hunt isn't limited to deep space. Some physicists speculate that if these black holes are abundant, they might still linger in our solar system, drifting unseen. Their faint magnetic wakes could perturb charged particles in planetary magnetospheres or even leave traces in ancient rocks. It's a long shot, but the payoff would rewrite physics. So while we marvel at supermassive black holes bending galaxies to their will, the universe's tiniest monsters might be hiding in plain sight, their quantum secrets encoded in the silent language of magnetism, waiting for us to decipher the message. What if the key to finding alien civilizations isn't listening for radio signals, but searching for cosmic-scale engineering projects leaking magnetic whispers? The concept of Dyson spheres, hypothetical megastructures built by advanced civilizations to harness a star's entire energy output, has long captivated astronomers. But instead of scanning for infrared heat signatures as traditionally proposed, there's a tantalizing alternative: hunting for the magnetic turbulence these colossal constructs would inevitably unleash. Imagine a civilization capable of encasing a star. Even with technology far beyond ours, the physics of energy extraction would leave electromagnetic fingerprints. Swarms of orbiting solar collectors, the more plausible variant of a Dyson sphere, would generate immense currents as they channel stellar energy. These moving charges would create fluctuating magnetic fields, potentially distorting the star's natural magnetosphere like a lightning storm inside a snow globe. The telltale sign: unusual polarization patterns in the star's light, or bizarre radio emissions at frequencies that don't match known astrophysical processes. One prime candidate already defies expectations: KC 8462852, better known as Boyajian star. Its erratic dimming, with brightness drops of up to 22%, sparked wild speculation about alien megastructures. While dust clouds remain the likeliest explanation, follow-up observations revealed another oddity: subtle but persistent radio bursts. Could these be the electromagnetic static of vast energy collectors rearranging themselves around their sun? The European Space Agency's Gaia mission has added fuel to the fire. While mapping stellar magnetic fields across the Milky Way, it flagged a handful of stars with inexplicable field geometries, ones where the expected dipolar pattern was warped or fragmented. One particularly puzzling case, Gaia DR340562911872, shows a magnetic field resembling a chaotic scribble rather than the smooth arcs seen in normal stars. When researchers modeled the effect of artificial orbital structures, the simulated distortions bore an eerie resemblance, but the real breakthrough may come from next-generation instruments. The Square Kilometre Array, set to become the world's most sensitive radio telescope, could detect the electromagnetic hum of a Dyson swarm's power grid, a symphony of synchronized currents across billions of satellites. Meanwhile, advanced spectropolarimeters might spot the unique light polarization caused by megastructures reflecting starlight through a labyrinth of magnetic fields. Critics argue that natural phenomena, like starspots or interstellar plasma, could mimic these signals, yet the search continues because the payoff would rewrite history. Finding a magnetic anomaly around a star wouldn't just hint at aliens. It would reveal how they harness the universe's fundamental forces. After all, if a civilization has mastered stellar engineering, their technological signature won't be a beacon begging for attention. It'll be the quiet, persistent thrum of magnetism, the universe's most versatile tool bent to an intelligence's will. In the deepest corners of theoretical physics, where reality bends into wild possibilities, there's a radical idea gaining traction that the same magnetic forces shaping stars and galaxies might also stitch together parallel universes. The concept hinges on brane cosmology, a framework from string theory where our universe is a three-dimensional brane floating in a higher dimensional space. And if these branes exist, magnetism could be the invisible thread weaving between them. Imagine two sheets of paper floating inches apart, our universe on one, another on the distant sheet. Normally, they'd never interact, but if space-time is threaded with ultra-powerful magnetic fields, these could theoretically warp the fabric between branes, creating temporary bridges known as magnetic flux tubes. Picture a cosmic wormhole, but instead of bending space-time, it's a tunnel forged by magnetism's pull, a fleeting corridor where particles or even information might slip between realities. The math behind this is as elegant as it is mind-bending. In some string theory models, magnetic fields confined to our brain could induce vibrations in higher dimensions, like plucking a guitar string whose echoes ripple into another world. These vibrations might manifest as phantom magnetic anomalies, sudden spikes in field strength with no apparent source, or particles appearing to gain energy from nowhere. One controversial study even suggested that the mysterious cosmic rays we detect with energies beyond theoretical limits could be trespassers from a neighboring brain, their journey enabled by magnetic tunneling. But the real wildcard lies in the quantum realm. If space-time is fundamentally foamy at microscopic scales, as quantum gravity suggests, magnetic fields could exploit this turbulence. Tiny, temporary bridges might flicker in and out of existence, connecting our universe to others in a vast multiverse network. Some theorists speculate this could explain dark matter's odd behavior. What if it's not just invisible matter, but matter leaking in from parallel brains through magnetic seams? Of course, evidence remains elusive. No experiment has yet captured a definitive signature of brain-crossing magnetism, yet tantalizing hints linger. Anomalies in Earth's ionosphere, like sudden unexplained plasma oscillations, have fueled speculation. Could these be echoes of a distant brain's magnetic storms? Even more provocative are lab experiments with superconductors, where confined magnetic fields exhibit behavior that some physicists argue mirrors higher dimensional leakage. The implications are staggering. If magnetic multiverse bridges exist even fleetingly, they'd rewrite not just cosmology but the very nature of reality. Time, causality, and the limits of energy conservation could all bend under the weight of cross-brain influence. And while the idea sits firmly at science's speculative edge, it's a reminder that magnetism, often seen as a local planetary scale force, might hold keys to the grandest cosmic mysteries. So the next time you hold a magnet near a refrigerator, consider this. The same force making it stick could, on some unimaginable scale, be the universe's ultimate connective tissue, binding not just atoms but entire realities in an invisible, multidimensional web. From the moment the first stars ignited in the cosmic dark, magnetism has been the universe's invisible conductor, orchestrating the grandest symphonies of creation. We've journeyed through 30 astonishing ways these hidden forces shape reality, how they cradle stellar nurseries, twist black hole jets into cosmic blowtorches, and even sculpt the gold in your jewelry from the ashes of colliding neutron stars. Magnetic fields don't just exist, they animate the cosmos, turning chaos into structure, silence into auroras, and emptiness into potential. They're the reason planets keep their atmospheres, why pulsars flash with atomic clock precision, and how dark matter might finally reveal its secrets. Think about the scale of this influence. The same phenomenon that lets a compass needle wobble toward north also launches galaxies' plasma jets across millions of light years. Magnetism stitches together the cosmic web's filaments, fuels the sun's deadly tantrums, and might even thread parallel universes like beads on a string. It's there in the quantum foam of space-time, where virtual particles dance to its tune, and in the depths of Europa's ocean, where alien life could be harnessing magnetic currents to survive. From the fiery hearts of Magnetars to the frozen whispers of primordial fields lingering since the Big Bang, these forces are the universe's quiet architects, building, destroying, and reshaping everything in their path. But here's the most thrilling part: we've only scratched the surface. Every discovery, whether it's a star with a magnetic fingerprint that defies physics or an exoplanet whose auroras glow in X-rays, rips open new questions. Could magnetic reconnection unlock clean energy on Earth? Will we find a pulsar's radio pulses encoding messages from alien civilizations? The answers are out there, tangled in the same invisible fields that have guided cosmic evolution for 13 billion years. Now it's your turn. Which magnetic marvel left you awestruck? Was it the thought of a magnetars pull liquefying planets, or the eerie beauty of Saturn's hexagonal auroras? Drop your favorite cosmic magnetic mystery in the comments. Let's geek out over the forces that bind the universe together. And if you're hungry for more deep space revelations, hit subscribe. The cosmos has endless secrets left to spill, and we're just getting started. Until next time, keep looking up and remember, the universe's greatest stories aren't written in light, they're etched in magnetism's invisible ink.